Hello everyone. This video we will be continuing from our previous sessions on characterization of invertible matrices. We talked about those 12 statements of IMT, and now we are going to do more examples on that. So the first example I'm going to do today is when is a square lower triangular matrix invertible? I hope you guys remember an M cross N lower triangular matrix is one whose entries above the main diagonals are zeros. So if we have an example here, say we have 1, need 0, 0, then we have 2, we can have any element here. So suppose 4, 0, need to make that okay. So we have here, so 2, this can be any element, this can be alien element, and say 1. Okay. Now, this is a special case I'm looking at. It's a square matrix and all the there's 0 elements on the diagonal. Now, so the solution to our answer is when this is going to be a square lower triangular matrix invertible. This classically is that case. It's a square matrix and all the diagonal elements are non-zero. The reason what happens is that we can apply our row reduction algorithm to it, and after we apply the reduction algorithm, we can create an equivalent matrix of the kind, say, so whatever the elements, so 1, 0, 0 would be there. So, excuse me, so we are going to create our algorithm such a way that we will now have elements here. These will be non-zero elements. You know, the square matrices, these are non-zero elements, guys. This is 0. And we will have, so we will have terms here because we are now creating an upper triangular matrix. So we'll have a row echelon form. Let me redo this matrix, guys. So 1, we will have some elements here, some elements here. These are non-zero, the square elements, if you guys remember. And then we will create an echelon form of it. Remember, these can be any element. Whereas these square boxes are non-zero elements. Okay, so the idea is if we are given a lower triangular matrix and we have non-zero diagonal entries, we apply a row reduction algorithm and we get an echelon form of it. And in a previous video, we actually talked about that if we have a square upper triangular matrix with non-zero elements on the diagonal, then it is invertible. So that's what I've written over here as solution. If I have a lower triangular matrix with non-zero entries, then these end diagonal entries can be used as pivots to produce zeros below the diagonal. That's what basically I'm talking about. And as a result, we will have end pivot positions. So this matrix is invertible by invertible matrix theorem. Let's look at more examples. Now, can a square matrix with 2 identical columns be invertible? Why or why not? The answer is no, it's not possible. Because if you have a square matrix with identical columns, then clearly those columns are linearly dependent. And by part 5 of the invertible matrix theorem, A is not invertible. Or statement 5, whatever you want to call. So let's look back at that. This is the one I'm talking about. So we will have to go back and forth between these two. So the columns of A form a linearly independent set. and hence this matrix A is not invertible. Okay, now let's continue with another example. Is it possible for a 5 by 5 matrix to be invertible when its columns do not span R5? Why or why not? Clearly, by IMT, statement number 8 is a false. And if you recall, statement number 8 says that the equation spans, if a matrix is invertible, then the columns of that invertible matrix must span R5. So clearly here, if these columns are not spanning R5, the matrix cannot be invertible. And hence our answer is a no. Now on to the next example. If A is invertible, then the columns of A inverse are linearly independent. Explain why. Now, if A is invertible, then we clearly know the inverse is also invertible. Now, by IMT, columns of A inverse are linearly independent. Now, this one is invertible not by IMT, but we already know from a previous section 2.2 that if A is invertible, A inverse is also invertible. Okay, so we need to cancel this one, guys, out. So that's not there. So if A is invertible, A inverse is invertible. And by IMT, because a matrix is invertible, columns of that matrix are linearly independent. On to the next example. If I have a 6 by 6 matrix and this equation Cx equal to V is consistent for every V in R6, then is it possible for some V this equation Cx equal to V has more than one solution? Why or why not? The answer is a no. The reason is the statement 8 makes the C not invertible. Oh, sorry, it's 7 here. Now what is 7? Let's go back over here. Now this problem says if a matrix C, which is 6 by 6, and the equation is consistent for every element V in R6, then this equation has at least one solution for each B. Okay, because the statement is saying in the problem the Cx equal to V is consistent. That means it has a solution for every B in Rn. So that's statement number 7 we are talking about. Okay. So if it is the statement C, it is invertible. Now, from theorem 5 in section 2.2, if the matrix is invertible, now we'll have to write C over here because we're talking of a matrix C. As the C is invertible, then for each V in R6, this equation has a unique solution. Now, clearly this means that you cannot have more than one, so this is not possible. Okay, continuing further. Explain why the columns of A square span Rn whenever the columns of A are linearly independent. Now, if the columns of A are linearly independent, by IMT, A is invertible. Now, let's look at this A square. A square is made by multiplying two matrices A. Now, A is invertible. That means product of these two invertible matrices is invertible. Theorem 6, section 2.2. Thus, A square is invertible, and hence by IMT, the columns of A square will span Rn. Okay, now we are going to look at invertible linear transformations. Now remember that if A is invertible, and then matrix multiplication also corresponds to composition of linear transformations. If my matrix A is invertible, the equation A inverse AX equals X. Now it can be viewed as this. So remember when we talked about matrix multiplication AX, we are viewing this as a linear transformation where X is being, affected or is being multiplied by A, and that can be seen as AX. So we are having a transformation which is given by multiplication by a matrix A. Now, if this matrix is invertible, that means we will have another matrix A inverse. When multiplied to this element here, AX, it will take us back to X. This is the things we did long time ago in linear transformations. Now we are applying linear transformations to what we are learning in terms of invertible matrices. Now, a linear transformation T from Rn to Rn is said to be invertible if there exists a function S from Rn to Rn such that the composition of S with T when acting on X gives us X for every X in Rn, or T when having a composition with X. Now remember, these are transformations. Acting on X equals X for all X in Rn. Important for us is this Theorem 9. Theorem 9 says if T Rn to Rn is a linear transformation and we have a standard matrix for T. Remember section 1.9 in chapter 1. That's where we're talking about. If I have a linear transformation, every linear transformation is going to have a standard matrix which corresponds to that. On top of that, if we say T is not invertible, now that is only possible if and only if A is an invertible matrix. In that case, I will be able to find a linear transformation S which will be given by A inverse X, and this is a unique function which satisfies this equation 1 and equation 2. Let's go ahead and look at one example in this concept we just learned about. Now, T is a linear transformation from R square into R square. We have to show that T is invertible, and we would then find a formula for T inverse. We are given this T linear transformation as 6x1 minus 8x2 minus 5x1 plus 7x2. I'm trying to write in this form so that it's much more easy to save space. Now, to find the solution, I have shown you all the little steps here. So T of x1, x2. Now, this can be seen also like this. As we are more, used to looking in terms of columns than rows. Okay. So when T applied on x1, x2 is basically 6x1 minus 8x2. Remember, this is the first row, and minus 5x1 plus 7x2 the second row. It's a column matrix. Now, if you recall back, you can write this matrix as this 1 by 1 as a matrix times another matrix. So this is the standard matrix A, and this is X. Remember, if T is a linear transformation, that basically means I have a linear transformation from Rn to Rn. That means Tx can be written as Ax, and this A is what is given over here. Okay, now we want to prove that this T is invertible. We just looked at the theorem again before, saying that if T is invertible, if and only if A is invertible. So if I want to prove T is invertible, just look at the standard matrix, prove that it is invertible, and then find out what T inverse looks like. Coming back to our problem over here. Now, T is a linear transformation. I have been able to write it as a matrix times a column matrix X. Now, this A, remember, is a standard matrix. We're going to prove that this standard matrix is invertible. Now, we have learned in section 2.2 of our book that this matrix A can be easily found out if this is invertible. Just look at the determinant. Okay, so when you look at the determinant of this matrix, the determinant is what? So determinant of this matrix A is 6 times 7, 42, minus 5 times minus 8, which is 40, which is a 2, non-zero. So clearly by the theorem we looked at in section 2.2 here, that determinant of A is non-zero, this matrix is invertible. Now, just from our previous theorem number 9 of section 2.3, T is invertible. And we just have to write down T inverse of X. Now, T inverse of X is nothing but A inverse of X. And we just have to find A inverse. Now, if you go back to your section 2.2, you will find that you can write A inverse as you write down the determinant. So if you remember, A inverse is what? 1 over the determinant of A times the inverse of the matrix. So this was the matrix 6, negative 8, negative, okay, let me just write it down here. Basically, inverse of A. Now, to find an inverse of a 2 by 2 matrix, we basically know we flip the diagonal elements and multiply the other diagonal elements by minus 1. So, and then you multiply by 1 over determinant of A. So 1 over determinant of A is basically a half, which is 0.5, 7, 8, 5, 6. And that's what you write down. So this is your A inverse multiplied to the element X, which is represented by this x1 and x2. And when you do the matrix multiplication, you get 0.5 times 7x1 plus 8x2, 5x1 plus 6x2. So we have been able to solve the problem. And I would like you guys to practice these following questions from the book. These are questions 1 to 8, 12, 19, 20, 23, 24, 27, and 33. Thank you.